Hello everyone, it is my great pleasure to join this mixed reality workshop virtually today and to discuss the potentials for using HoloLens and other mixed reality device for automated mobility assessment. I would like to thank Melvin for inviting me for this session and thank you all for attending this section. I was at the mixed reality workshop in 2017 ISPGR, and this workshop inspired me to work on the HoloLens device and achieve this research progress. And I'll definitely hope after today's session, after more people has hands-on with the device and we demonstrate the potentials for this thing, we could have more fruitful research outcome from this line of research. Also, a special shout out to my previous lab where I work at the University of Illinois as a postdoc. So majority work discussed today was done at the UIUC lab. Although I'm currently at the Wearable Health Lab at Stanford University, and I'm continue innovating in different kind of technologies, wearable device for health and mobility tracking. So today's discussion will be primarily focused on the feasibility, validity, and the limitations of using HoloLens for this conducting automated mobility assessment. And we also have a poster that will be hung up at poster session 1, W182. It is a detailed discussion about the validity investigation using the HoloLens for mobility assessment, which I will briefly touch on in this talk. But for details, please go to the poster session. All right. So a little overview about today's session. So first, why using the AR or also augmented reality or mixed reality device for mobility assessment, and design challenges we encounter for developing for older adults to use independently. We also gonna talk a little about the measurement validity and the lessons we learned through this progress, and also discuss on the room for improvement. So to begin with, why are we doing it for using the AR device for mobility assessment? Well, many IMU device has been proven to be useful for clinical mobility assessment, such as time of a go, 6-minute walking, sit-to-stand, etc. And all the wearable device can be wrist mount, phone, cell phone, or foot mount, or put it on over the lower back. So for example, the Oppo sensor we use here can be put it on different spot, and then it's very small device that can record the movement. However, all these sensors are often still used as a recording device alone that still require additional personnel to operate it and also guide the user, right? So all the tests, we still need an extra person to talk to the patient or participant to through the protocols and then perform quality checking and all that. So the setup and instruction and demonstration took a lot of time and effort for the research personnel or clinical personnel, thus preventing efficient clinical implementation. So what if we can have a standalone device that can do both recording and guidance automatically? That's our overarching questions in using this AR/MR device. So why using the HoloLens device? What's the benefit specifically for the HoloLens? So firstly, it has built-in visual and audio modality. So you have visual display on the visor and also microphones that allows for instructions and demonstration to be placed on the device. So user can receive those without any external device. Secondly, it has nature user interface through gesture control, gaze control, or voice control. So it gave us a way for user interaction. So not only the user can receive instruction and demonstration, they can click on the buttons or notice the app to proceed or select or change. One special note about the gaze, which we use for our research project. It is an estimate gaze. So instead of the true gaze with camera facing the pupil, it is IMU, or the head orientation estimation. So basically choose the center of the head orientation as the gaze. So imagine you have a laser pointing from the middle of the eye, and that's your estimated gaze. Next, it has full visibility of surroundings. So unlike the VR device that block your entire field of view, this one allows you to see it through, and it allows for safe navigation of the environment. And because it's also a standalone device that has computation power on the chip itself, it doesn't require any additional PC, laptop, or Wi-Fi dependency. So it gives you the freedom of movement to anywhere as you wish. Okay, indoor, outdoor, it doesn't really matter. Lastly, it has a built-in IMU and depth sensor for users' head tracking. That provides us a mean to accurately track head movement and then infer their mobility performance during the clinical test. So all in all, these four benefits of the HoloLens device make it an ideal device for conducting automated mobility assessment. Is to design the app based on the HoloLens device to make older adults use it independently. So our goal is to have an automated test, and but we have to design it for the older adults so that they can use it. So the design challenge we encountered, of course, with aging, we all know that they have poor vision and also have a hearing decline and poor perception, depth perception. And a lot of people, who, especially with the advanced aging group, they don't have much of the technology proficiency. So some of them we have seen use smartphone, but a lot of them are not really using any of the technology device. And additionally, you should expect that older adults should have some mild cognitive decline. So when you're dealing with patient communication, usually we speak slower and also repeat our instructions. So that's something for technology we also have to account for. And lastly, because the device is heavy, as you may have already had hands-on experience, and with aging population, they have general chronic condition with neck and back soreness, and also because this new technology, we want to preventing for motion sickness, this sort of thing. We have to adjust for our software or app development to make it like shorter period of use. So our design solutions to these design challenges are first using DesignMeister to maximize the color contrast and font size to maximize the visibility, and to account for hearing decline and people using hearing aid. We default to maximum volume of the device, but if people are using hearing aid, we'll tune the volume down, because you have to be considerate on the hearing aids. And next, with depth perception, what we have is space anchor display and the physical mark on the ground. So with space anchor display, basically you have a target or display lock into a physical surrounding. So lock into a wall or to a certain distance away from the participant, rather than the display will drift with your headset. So if you turn, the display or the target will stay on the fixed spot rather than it's moving. And the physical marks on the ground. So for example, for the time up and go test, we actually tape the ground saying 3 meters away, and ask the participant to cross the line and turn around, rather than actually drop a box or tape, virtual tape on the through the display, we choose the physical marks because we think the virtual ones, because when you walk past it, it will become like disappear, or because it's under your foot, though it's going to be out of your visual field, it will make some confusion to the participants. So rather, we want to have physical marks on the ground. So by combining the virtual ones versus the real physical marks together, we created this test walkway for them to complete the test. So that's some design solution we have. And additionally, we have our display within the horizontal field of view, so basically centered to the participants' nature field of view, rather than ask them to search for things outside their view. This is particular designed for older adults who doesn't really have technology proficiency, so they won't, like young adults, to search through the room to figure out a different box or something. Everything has to be directly in front of their field of view, so that they can see it and select it. Additionally, we have redundancy in information, so multiple modality have video demos as the task we wanted them to do, audio instruction plays through the video, and text reminders to cue them to do the task, and plenty of prompts and cueings during the test to stand up, turn around, sit down, or are you ready to begin, or do you want to repeat, this kind of thing. And also choose clear shape, size, and color differentiations between buttons, displays, and instructions to make sure that they can have the clean message of the instruction. Additionally, we decide to use the gaze interaction to control the app rather than gesture, because the gesture control, like pinching the fingers, it is very hard for the older adults to acquire the skill and then adjust for the interaction method, especially with the depth component added in. So we decide to use a gaze interaction. So anytime when you fixating your gaze to a button, that demonstrate your intention to select that button. Okay, and additionally, we have lengthy, or I'll say comprehensive user onboarding process. Demonstrate to the participant how to wear it properly and what to expect when you put it on. So what's the see-through. And also, we minimize the wearing time to no more than 10 minutes, and usually the test should be able to complete by 5 minutes mark. So, but of course, user onboarding takes longer time in that case. All right, so here are two screenshots from the software development, Unity software. You can clearly see we choose a dark background and green font as the display. And the reason we choose this two color is to have the maximized contrast, so that when you put the HoloLens on, you can still see the display. So the dark background, although here is completely dark, when you put it on the HoloLens, you can see through it. It's just basically added a curtain sort of thing, so that when you are using the device and facing a different color, say a wall or a door painted in yellow color, it is not completely make the text disappear. All right, so we also choose the white buttons as the control button. So here, the center here is a white color, so there's direct contrast to the background that is visible. And the purple gaze cursor, that is dynamic, that when you move up and down, it follow you. And when you are not, I'll say we call collision with the object, so you are not really pointing to an object, it's a fuzzy one. However, when you actually colliding with an object, so this case is a video screen, or you're colliding with a control button, it will change it to this ring shape and indicating it's now focusing on. And after you focusing on for more than 2 seconds fixation, it will trigger as a selection. So basically look at here for 2 seconds, it will trigger as ready to start. Okay. All the display are designed to be all from within the horizontal field of view. So basically everything within the center field. We tested out and find out because the inexperience with technology, when older adults put it on, they won't actually look up, look down to search for different information. Everything must be directly in front of them, centered. Otherwise, they won't even understand. So they don't have a natural tendency to scroll up or scroll down to look for more. So everything must be within one center display. But it make it more challenging because different person put it on differently, and some people the top line may be clipped off. Some people may actually clip off the bottom part. So what we have is we have an additional couple steps of field of view calibration after putting on. So essentially we have this center box. We test it out and put it in a center spot that we asked our participant to adjust their headset and chair seated position so that when they look straight forward naturally, so seated still, look straight, their gaze should naturally fall within this bounding box. And lastly, we also have this auto adjusted for seated and standing position. So all of it should be right in front of you, no matter whether you're seated or standing. So a lot of tests, we started from the sitting position, and but for others, we may have a standing position to begin with. Additional step for user onboarding, we showcase a pre-recorded demo video, which I will show in the next page, and to ask participants to watch it and ask questions to understand the procedures. And also we have provided a live streaming screen demo. So basically they will see a computer screen where we are demonstrating how this thing works and showcasing it before hand it over to the participant. Alright, in this video, it's a direct video demonstration for our participant to get familiar with the procedure and also demonstrate our test functions. So, let's see.
Please watch this video demonstration. Please sit in this chair and put your arms by your side. When told to start, please stand up from the chair, walk toward the line on the floor at your normal pace, turn around and walk back to the chair and sit down.
Okay, so to walk you through step by step, what you have first is the on-screen demo of the task, and you will see the video display of the task and text message on the side, and the audio instruction play through it. And afterwards, after the demo went through, you will have options to select to repeat the video or focus to start the test. These two buttons in different shape and different position, and for all the tests it's the same layout, so it's a consistency across different tests. And after you fixate your gaze into this spot for more than 2 seconds, it will start the countdown procedure. So you will have a note saying standing up in 3, 2, 1, and you will hear a ding sound to notice you to start. So both video and audio cueing. And afterwards, everything disappears to minimize the motion sickness. So people perform the task, and afterwards, when they sit back on the seat, we will have the notification to ask you to continue to finish the task. All right. So we have a validity investigation that is published in Sensors and also in this poster session. So what we have is mounted 2 additional Oppo sensors, one on lower back and also mounted on the head. So basically tape it on the HoloLens. So ideally they should register the same signal, and we want to compare their signal agreement. So we recruited 10 older adults and 12 young adults, and we asked them to perform 5 times sit-to-stand and time up and go test. And we measure the signal agreement with cross correlation and normalize the root mean square error. General finding is our better signal agreement observed in the sit-to-stand task, as each sit-to-stand cycle allows for displacement calibration. And however, for the time up and go test, because there's only one sit-to-stand cycle, it is harder to calibrate during the middle portion, and that's resulting higher tracking error. And we suspect it's from the Oppo or the IMU sensors rather than the HoloLens sensors. But for details, you can refer to the poster session and paper, and I will briefly discuss the take-home in the next slides. So the lesson we learned through this investigation pilot testing is for the sensors of the HoloLens, raw IMU sensor data from HoloLens is not available. So what it provides is a so-called camera or head position data. So it is already fusioned of IMU and depth sensing, and it's account for the drift of the IMU signal and also the integration error. So we tested out and found that, the calibrated or the fusion data is accurate. However, because we have IMU, the Oppo sensor we had that suffered from the drift over a long period of time, we cannot really conclude that is the HoloLens is actually better than IMU, but we suspected that's the way. So additional step with optical motion tracking should be conducted to truly validate these outcome measures. So also because the device is sampled at the varies with the Windows clocking. So essentially it is sampling at around 30 Hz, but it's not precise at 30 Hz. When I first developed the app, I saw it's because the parameter I set is 30 Hz, so I assume each individual frame in between is 1/30 of the seconds. However, it is not the case, so I have to redo it, recollect the data of the having the exact timestamp on it, and then later resample it to 30 Hz or 60 Hz, this kind of thing. So that's a lesson we learned through this procedure. So if you are planning to record data from this, make sure you notice this kind of potential issues and avoid these pitfalls. Additionally, one of the biggest problem we encounter are the data loss due to depth scanning. So to be more specific about this is we test our older participant in a small apartment room to test the feasibility. So we went to a retirement center and tested out. So this small apartment has very small size. So when the time up and go test was set up, it's basically they walk to a wall and turn around. So basically face against the wall and before turning around. In that case, when you are approaching the wall too close, the system may reset because the depth scanner failed when it's too close. So that causing the system reset and then causing the gap in recording. So every single time when they are approaching the turn, there is a missing gap, half second or so. And then when they return, we see the data back on. So I have a lot of trouble at the beginning to figure out what's happening. Until one day, I think I talked to Melvin through Twitter and checking on this, and then he pointed me out this direction, and that until you do it, you wouldn't even know it, right? So that is a big pitfall when using this device in a small space. And so that's one big lessons we learned with the sensors. And additionally is through the voice command, we eventually have to disable it during the test user onboarding process, because every single time during our conversation, if we mention start and stop, it will trigger some behavior with the device. So the problem with that is setting up the HoloLens. So loading the app and anchor it to space, this kind of thing require research personnel to do it. And once we set it up, we basically set it up in a location, and then we hope that the participant should put it on and be able to see it with minor adjustment. However, during our onboarding process, some keyword may be mentioned, and that reset the system, and that causing our prior setup completely fail. So these are something that you should consider if you are trying to use it with sort of a conversation with the participant, and that may trigger something that unexpected. All right, and lastly, standing balance assessment with basically eyes open, eyes closed is not viable using this device. We originally developed this app to measure standing balance as well as time up and go and sit to stand. However, because the headset weight and using the gaze control to select the buttons, the small movements of the head, maybe causing by the height weight or the gaze control, like nodding your head to look for some buttons, that affects our recording quality. And even though we have a middle section that is somewhat quiet, we basically fail to differentiate the sway differences between eyes open and eyes closed. However, our lower back sensor can definitely pick it up, the difference. So that's this head sensor, or especially this heavy device that is using the gaze or head movement to control the unit, is not a viable solution for this subtle change differences between balance assessment. So that's some take home from the sensor side. Also from the user side, that's a lot of different lessons as well. So first time user onboarding is definitely challenging. So we need 10 minutes or maybe even more to help the participant to put it on correctly with proper field of view visions. And also because we have this system reset, because voice command at the beginning, it takes a long time and causing user frustration at the beginning. But after you went through all that, the test can be done fairly quickly. So 5 minutes time, you can complete sit to stand, time up and go, and we also conduct the balance assessment test altogether, but it takes less than 5 minutes altogether. So and also older adults with severe cognitive or mobility deficit could not complete the test independently. More specifically with people with severe cognitive deficit, so they have trouble to memorize the procedure, and so if it's a real person test, you as a researcher, we probably would constantly reminding them to do certain things. Now please stand up as fast as you can and do this kind of thing. However, with the technology, they cannot really detect the subtest, the failure, saying you should do quicker, you should do slower at your normal pace, this kind of thing. So it is we want it to be used automatically or independently, but if we have to engage as a researcher, basically it's failed its purposes. Similar thing is for the people with mobility deficit, because the device is kind of heavy and people are sort of afraid of it to fall off. Certain time when this become sit to stand task or it's challenging, certain people has a tendency. So first is using the arm rest to stand up. That's one way that is the device cannot detect whether you are holding your hands properly or actually touching the side of the arm rest. Secondly is people kind of has a tendency to grab the device to make sure it doesn't fall off, but that completely change your quality of device. So essentially when people look down or something, they kind of using your hand to hold the device. That also failed the device recording. So that's kind of two user scenarios that older people with various deficit cannot complete the test independently. All right, and also, well, the majority, 8 of 10 older adults report discomfort of the headset because it's heaviness, tightness, and fit for glasses. So, and we have some quote here, and also a steep learning curve in learning how to move the head with these gaze control. So again, we have people quoted saying, if I can do it, it's hard to learn it first, but afterwards, if I do it second time, it could be a lot easier. But yeah, this is the user case that the onboarding, the steep learning curve, and the discomfort with the device, that is still a challenge for the using this device for automatic independent test. Okay, so lastly is about the room for improvement. So based on our take-home message, we noticed that the user comfort is definitely a big challenge. So a lighter device and have a larger field of view and with easier adjustment would be definitely appreciated. Luckily, the HoloLens 2 is just getting on the market now. So Microsoft realized this same issue, so they are making it more easy to fit with glasses, put it on, put it off, and a larger display area, and also balanced design, so it doesn't really feel that heavy, and it allows for easier adjustment. However, based on our user scenario, we're not really for gaming or live streaming anything. So we actually use a very low fidelity of the display. So rather than a 3D object or dynamic changing environment, it's more like just a display, and then the people will do it and we'll measure their performance. So some low fidelity device, for example, this recent one called Focus by North. So basically a smart glasses or Google glasses that you can have some display on the screen, or video or audio instruction placed through the microphone through this device. That would easily meet our goals, and that would be lighter, portable, and less burden on the participant, and maybe can be used with a better user experience. For our research world, I think what we need to do is to continue our research into comparison of head tracking to mobility, to extract mobility and gait features. So because we have, extensive work has been done with wrist mount, waist mount, feet mount sensors, but the head mount sensors, we only have like a selected few, and the trade-off between the sensors need to be investigated. So maybe we'll have a better user interaction through the head mount device. However, the of course sacrifice a little on the gait features accuracy, this kind of thing. But in all, I believe this head mount device can be a potential for future mobility tracking, as it can be more intuitive to use with glasses in this kind of setup. Additionally, we should consider the clinical applications when we are developing these kind of device. So we have to consider the test environment, the room size, the indoor-outdoor environment, and then test protocols like populations. So if most people are with severe mobility deficit or cognitive deficit, it may not be safe for them to use it, so there's no point of using it. However, if it's for general physical screening or fall risk assessment in the community, serve as a triage tool, that may be a beneficial user case for this device. And additionally, we need to develop real-time analysis calculation on the chip and reporting directly to the physicians. So basically, more feature extractions and more understanding on what we measure through the head mount device, and then can be fast calculation to meaningful features and reporting to physicians to guide clinical therapeutic interventions. Lastly, with this potential low fidelity device, it may have a potential to be used in free living mobility physical activity tracking, and maybe have better user adherence case. However, given this the novelty of the device or the potential issues come with privacy and security, those are things that need to be considered if it is designed to be used in a free living environment. All right. I'd like to extend my special thanks to my former lab members from the Motor Control Research Lab at UIUC, my postdoc mentor, Dr. Jake Sosnoff, for the guidance, the funding support from the CHART seed grant from UIUC, as well as Microsoft for lending the device for our research use. I'd like to also extend my special thanks to Melvin and ISPGR for the 2017 Mixed Reality workshop. Through that experience, I got the first hand-on experience with the HoloLens and getting very excited and inspired to my current line of research. I'd hope by today's talk and also this workshop, I will hope to inspire more people to join this research field and also foster some collaboration down the line. With that said, even though I'm not here today, and if you have questions, please feel free to reach me through my Twitter account and also my email at stanford.edu. The code for data recording is available on GitHub, so you can send me a request and I'll forward you the link. And however, because this project is the intellectual property of UIUC, so only a portion of the data recording part is available. The poster section is again P1 W182. If you are curious about the details about validity investigation, please stop by. Even though I won't be there, there are further information there and also video demos through YouTube. With that said, I want to thank you all for attending this session and hopefully to have a future connection with you all. And thank you so much.